Thank you for watching the AI Weekly Update series from Henry AI Labs on the week of June 16th, 2021. We have a lot of really interesting viral style content like OpenAI is improving language model behavior by training on a curated dataset. And then I think Google's reinforced learning designs TPUs, the reinforced learning for chip placement. But I think overall the most interesting technical paper this week was Generative Models as a Data Source for Multi-View Representation Learning. This is exploring the paradigm where we have taken a data set and we've compressed it into a generative model. So say we've fit a generative adversarial network on some data set, and now we have that generator component that we can use to generate data and use that data for this as the data source for this self-supervised learning. So what they're doing is they're using this for contrastive learning, where they use the distances in the latent space to form the positive and negative pairs, and they get a really interesting result using this generative sampling as the data source. And then a similar study, learning to see by looking at noise, extends the study further by, say, looking at fractal images or wavelet images that match, say, like color histogram, frequency distribution kind of features in the generative models to produce the data sampling procedure. Next up, we have two interesting studies about knowledge distillation. The first of which is knowledge distillation. A good teacher is patient and consistent. Looking at knowledge distillation through the lens of model compression, where we want to take a large model like the BIT large models and compress them into, say, a ResNet 50 for the sake of inference and storage costs. So the idea behind patient and consistent being that the teacher and the student should look at the exact same view of an image. So say you're taking an image, you shouldn't have two random augmentations passed to the teacher and the student. They should see the exact same view. And further, they use the mix-up augmentation to increase the support of the data distribution and help with overall the views that are used for distillation. And then patient is referring to how these benefit, the knowledge distillation process benefits from long training schedules. And then the next paper is, does knowledge distillation really work? And this is a very interesting question, showing that even though when you have this distillation where the student is fitting the soft label distribution of the teacher, it actually isn't doing a very good job of matching the teacher. Matching the teacher's predictions is a very hard task. So even though it's improving generalization, it's not actually achieving this task they dub as fidelity, which is actually matching the teacher's distribution. Next up, we have AdaMatch. AdaMatch is the next installment in the series of papers from Remix Match, Fix Match, and now AdaMatch, looking at the cutting edge of semi-supervised learning, where we have a small labeled data set and then a large unlabeled data set, and maybe some of that unlabeled data is labeled and so on. And AdaMatch is looking at bridging the gap between semi-supervised learning and domain adaptation. And domain adaptation, we might treat the source and then we have the target. So we have two different data distributions. So say we're first training on cats versus dogs, and then we're transferring to something maybe as dramatic as it could be like dinosaur classification. Some other kind of domain shift is the idea behind domain adaptation, difference between the source and target distribution. So this is saying that in semi-supervised learning, it's really the same setting where you have the small labeled set and the large unlabeled set as this domain adaptation problem. So they take the fixed match algorithm where they have this pseudo labeling, consistency, distribution alignment with the class labels that are being pseudo predicted, and so on. So we'll get into the details of the AdaMatch algorithm, adapting it for domain adaptation as well. The next paper is self-damaging contrastive learning. And this is very interesting, building on this paper that says, what does compressed neural networks forget? So as we prune neural networks, and the accuracy doesn't change much. You prune a neural network to, say, 5% sparsity, and the accuracy might go from 80% to 77%. Well, what exactly are the 3% that's being lost? And what they show is that what's being lost is the long-tailed distribution of the images, and especially in self-supervised learning, where we have this long tail of data, as we've looked at previous papers in the AI Weekly Update series, like divide and contrast. So this is looking at this structure of looking at what's been forgotten with pruning in order to structure the loss for contrastive learning, and this helps with these long-tail distributions for self-supervised learning. Then we have mass self-supervised transformer for visual representation learning. This is looking at a new strategy of how to apply the BERT-style denoising autoencoder task for pre-training visual transformers on, say, ImageNet or whatever vision domain. So the novel idea in this paper is to use the attention map to try to guide how you're going to mask out the tokens. You don't want to just randomly mask out tokens. Maybe you want to mask out windows, kind of like the dropout augmentation or the cutout augmentation and so on. So it's looking at a new strategy for how we're going to mask out pixels to try to apply BERT-style pre-training to ImageNet and so on. So the next paper is data efficient instance generation from instance discrimination. This is the task of trying to learn a GAN with only, say, 2,000 images, trying to learn generative models from small data sets. And the approach in this paper is to have a second loss function where you try to push all of the images to distant points and make everything dissimilar from each other. And surprisingly, maybe not surprisingly, but it doesn't seem like that crazy of a loss function to add, but it does have some pretty interesting results, improving over, say, the paper from NVIDIA on the discriminator goggles and applying data augmentation and all these techniques at advancing the state of learning a generative adversarial network with, say, only like 100 or 500 or 1,000 images, which is much more realistic for a lot of these applications for GANs. And then also maybe ideas like this, where we're trying to use the generative models for a data source for self-supervised learning. It would be interesting if we could learn them with less data. Then we have new advances in neural architectures, the first of which is the new ImageNet state-of-the-art by scaling up vision transformers to 2 billion parameters. Interesting lessons along the way, the same lesson from natural language processing of it's better to train a larger model and then compress it. Given your compute budget, it's probably best to scale up the model size, and some other details of the performance and then the training strategies of training this at scale. And then another architecture, CoAtNet. CoAtNet is a combination of, it's a depth-wise convolution over the self-attention, one of these subtle architectural changes that results in interesting performance. And two very interesting new architectures for computer vision have come out this week. Then we have a couple new advances from language models from OpenAI, improving language model behavior by training on a curated dataset. The curated dataset that they note is 120 kilobytes, which is significantly smaller than the dataset used to train GPT-3. For reference, say the Pile dataset that's used to train GPT-J is trained on 400 gigabytes out of the 800 gigabytes in the Pile, so 120 kilobytes is a much smaller data set. So it's interesting that they're able to steer the behavior by fine-tuning it on this much smaller data set that they use to try to have this problem of avoiding toxic outputs and bias in the language model outputs. So then the next paper is Dynamic Language Models for Continuously Evolving Content. This is a very interesting paper that covers this problem of, say you model a language model on Twitter data from 2013 to 2019, and then you're generalizing it to 2020, 2021. There's going to be a new vocabulary, semantic concept shift. So it's a very interesting problem of thinking about how to update these language models. Obviously, you don't want to have to completely retrain them from scratch, and there's all sorts of research like early on the net-to-net paper that is trying not to throw away these models when you're trying to retrain it because of how expensive it is to train it to begin with. And this is a building on that idea, and particularly showing the problem with evolving content on Twitter with new vocabulary and then semantic concept shift. And then also in the space of natural language processing, the GPT-J model is now 6 billion parameters, the largest open source GPT-style model out there. They document how it was trained on 400 gigabytes of text. Other details, you can play with the prompt. There's a collab notebook and a web interface. You can test things like, say, zero-shot generalization or what they call few-shot learning, where you have the examples in the prompting context, and so on with this new GPT-J model. Then a new survey on data augmentation for limited data learning and NLP. This covers classification of 4 different levels of, say, token level, sentence level, hidden space, and one other that I'm forgetting right now, but different strategies for augmenting natural language processing datasets, and then reporting some empirical studies on how this is improved across all these different tasks in NLP, like text classification, natural language inference, question answering, summarization, and so on, and particularly how data augmentation has played a role on all these different tasks in natural language processing. Next up, we have an interesting new paper in the space of meta-learning with fewer tasks through task interpolation. So one strategy for data augmentation is mix-up. Mix-up is where you take 2 images and then you average together the pixels, average together the labels for each of the images, or in 2 text sequences. Again, you just randomly sample which of the words from each of the sequences you're going to blend together to form this new sample. You could do this in the hidden latent space, and so on. This is the high-level idea of mix-up. So they're going to be applying mix-up at the meta level of tasks as you're doing meta learning. Meta learning is where you say you have the omniglot data set, you sample, say, like 5 of the characters, and then you assemble new labels for them and have this new alphabet, and it has to try to learn the new alphabet characters quickly, ideally. So it's learning to learn quickly is usually what's meant by these meta learning papers. So you have, say, 5 examples from each of the new alphabet characters and sampled from omniglot, and then it has to learn that. So each sampling of these character sets for omniglot would represent a task. So you have all these different potential tasks, and then you can mix up between the tasks. And then they describe how, say you have label sharing or don't have label sharing, is an important detail for how you're going to interpolate the labels as you apply mix-up at the task level for meta learning. So a bit of a meta idea here, applying mix-up at the task level. Then we have out-of-distribution detection, exploring the limits of out-of-distribution detection. This is showing that these pre-trained transformer models are better at out-of-distribution detection than their predecessors are, describing the difference between near OOD and far OOD, say Street View house numbers and MNIST compared to ImageNet and Street View house numbers and stuff like that, and these kind of details. Then some interesting ideas in the space of unifying causality, causal learning, causal inference, and deep learning. So these two papers, self-supervised learning with data augmentation, and then provably isolates content from style, causally motivated shortcut removal using auxiliary labels. These are two, in my view, pretty similar ideas that where you're trying to disassociate this latent variable of content and style. Ideally, you could blur out style, enumerate the entire space of style such that you have this causal factor that attributes the content of the data with the label or whatever it is, and you could separate out content and style, content and say the confounding factor of style. So the idea here is to be able to sample different data augmentations to do causal learning, and then this idea is to use auxiliary labels to try to separate content from style. And in this case, it's more like content and label, I guess, but I don't completely understand these ideas, but I do think this space of this causal inference structure is going to be really important for deep learning. So then we have probably the big viral headline, the big advancement of AI this week is reinforcement learning designs TPUs using the reinforcement learning and graph neural networks for representation learning of the chip placement structure and learning this task. I'm not an expert on this particular problem, but it's an interesting idea using graph neural networks for the representation learning of how the, I think, transistors that they're packing onto the chips are connected to each other, and then using the reinforcement learning to structure how quickly they can design these boards to optimize the efficiency. And I don't know too much about this, but it definitely seems like a big step forward for, say, this recursive AI where the AI builds itself and so on. Then we have pre-training representations for data efficient reinforcement learning, and pre-trained encoders are all you need. These are two similar ideas. This one is exploring, say, 3 different self-supervised learning tasks for doing the auxiliary representation learning. So in my view, the foundational paper on this is, well, there are a few, but there's a paper titled Curl, where in Curl what they do is they pass the representations of, say, the Atari DeepMind control suite, the visual observations for control tasks, into the momentum encoder, the MoCo representation learning algorithm, and then they also pass that same representation into Q learning. So there are 2 loss functions. There's the Q learning, reinforcement learning, and there's also the auxiliary contrastive self-supervised learning. So they're using 3 different self-supervised learning tasks in order to improve data efficiency for learning these representations. And then in pre-training encoders are all you need. I think they're really doing the similar thing of exploring the self-supervised learning, but also I think it seems like maybe more so in the transfer learning setting than this one is. So then some new advances in code, the CodeXGLUE. I think this is a really interesting paper, past weekly updates looking at like the apps challenge and then deep learning with code data, bug detection and repair, all this stuff. I think this is a really exciting area. And the CodeXGLUE benchmark has different things like code repair, natural language mixed with codes, let's say documentation search or maybe documentation generation and these kind of tasks. So these are now available in the HuggingFace Datasets library. And HuggingFace also has released a course explaining different ideas like the auto model, pipeline, tokenizers, all these different ideas in the HuggingFace library. So then we have a new code example demonstrating how to do neural structured learning. Neural structured learning is where you have this like a different loss for, say, it misclassifies a dog breed as another dog compared to a cat and so on if you have these fine-grained hierarchy of labels. And then a code example of how to do zero-shot classification with the HuggingFace pipeline and other things. So HuggingFace has released a lot of videos since this came out earlier in the week, and then this came out, which if you're interested in either of these things, this would be the thing to do. Then some kind of applications in new data sets, audio to video synthesis, pretty remarkable ability to go from audio data into John Oliver presenting the audio data. And I've never worked with audio data before, so I don't know too much about this, but this seems like a pretty interesting advancement. Then this is a very interesting picture of GPT-3 versus GPT-Neo, looking at the data compositionality. So it's a diagram where we'll just look at it later in the video, so you can skip ahead if you want to see that. Text to SQL in the wild, a new data set of going from natural language to database queries, or what I think would be interesting would be the other way around, where you wouldn't even need a database schema. similar to last week's paper, database reasoning over text, but maybe that's too grandiose. Then value a multitask benchmark for video and language understanding evaluation, another data set for video data understanding. That concludes the introduction to this AI Weekly Update. Following will be a more technical view of each of these things. And then as a quick reminder to address some of the different comments, if you're interested in the links to each of these things, they are under the description of the YouTube video. So under the YouTube video, if it's maybe compressed in the video interface, you see show more and then content links. And then the links to each of these papers will be in the description of the YouTube video. We'll start with my favorite paper this week titled Generative Models as a Data Source for Multi-View Representation Learning. So we have these generative models like generative adversarial networks that can take a data set and then learn how to generate images from the data set that are realistic looking. So we can sample from this generative model in order to get data for then the contrastive learning that's used in, say, SimCLR, MoCo, and so on. So one interesting question that you might have might be, say that the generator is already learning a representation of the data. So say you have the big ByGAN framework. The big ByGAN simultaneously learns these latent space codes, learns how to predict the latent space codes from the generated image. And then you could argue that the latent space code is already a good representation of the image data. So you have the loss function on the generator and then the loss function on predicting the latent code that produced the image. But what this is showing is that if you add this intermediate step of contrastive learning with the generated data, it does improve the performance. And it's an interesting kind of framework of thinking about first generating data and then using contrastive learning with the generated data for the overall task of representation learning with, say, unlabeled data or labeled data. So then that's the next detail of this paper to present, is the difference between unlabeled, unconditional generative models and then conditional generative models. So this is showing the distinction between examples from the unconditional sampling and class conditional data. Say you study the conditional GAN. The conditional GAN takes as input the class label to produce as well as the latent vector Z. So say you have CFAR10, it'll tell it generate a deer or an airplane. So it won't just generate any image from the randomly sampled Z vector, it'll also condition it. And the benefit of that with respect to contrastive learning is we also have frameworks like supervised contrastive learning where you use the label in order to structure the positive negative view pairing. So it's an interesting detail as well, whether you use the labels or don't use the labels for this kind of representation learning paradigm. So they also discuss different ways for sampling from the latent codes. The latent vectors, these are how you're generating the positive and negative pairs based on the distances between each other, as shown in these diagrams with respect to the distance between the latent. So say the latent vector is very similar to another one. Ideally, it would change smoothly. So say you've seen the StyleGAN2 interpolation space. The reason that you can animate it like that is because the changes in the Z vector don't cause it to sharply change. So you can just kind of like animate it talking, say, by just moving around the Z space. So nearby Z vectors should be positive views in the contrastive learning framework, and then distant Z vectors should be the negative samplings. So overall, I think it's a very interesting idea, some interesting results, as you can see from the representation learning, comparing with real data with this. And I don't think it's something that's going to be completely groundbreaking yet with the results they present, but overall, I think this idea is incredibly interesting. Next up, we have learning to see by looking at noise. In the last paper, as we look at generative models as a data source for representation learning, we have a generative model that's fit real data compared to this paper where we're looking at noise. So in the past AI Weekly Update video, we looked at the fractal database where you have these procedurally generated fractal images that you can also use for contrastive learning. You could generate fractal images and then have some way of doing positive negative pairs. It could be the same exact data augmentation procedure that's used with real data in SimCLR or any of these ideas. So this idea is exploring further, do we need this the generative model data to actually be real data? So they're looking at these statistical generation models. They have the fractals DB thing is brought back. Dead leaves, which the way I understand it is you randomly assign squares onto different coordinates. They have their n for how big the square is, and then you generate the image, and then you iterate on this until the entire image is filled with a square or a pixel from one of the squares. So that's what I think the dead leaves algorithm is. The spectrum wavelets. I think this is about, say, when you have a Fourier transform of the image, or you have these color histograms. You have these generative procedures that match these statistics. So they have a similar sampling frequencies so that they can produce images that are identical to real images when you plot like the distribution of frequencies on a Fourier transform or something like that. And then these are two simulated environments. So say the sim to real thing, we have the clever benchmark where you have these generated objects in the space, the DM lab, and then Minecraft. So exploring other simulated environments that are synthetic data compared to using real data for self-supervised learning. So they further describe all these different statistical models, comparing them with the style GAN model with the real data, or I think even they just use a style GAN that's been randomly initialized. So they randomly initialize a model and they sample from it with these different sampling techniques like this uniform sampling over this interval and so on, and these kinds of ideas. So they show the performance, the accuracy of these different data sets. It looks like the dead leaves and so on don't quite match the ImageNet and so on, but still interesting comparison. And overall, I think this paradigm, they argue in the paper, I'm not sure if it was this one or the last one, talking about what might be the benefit of doing self-supervised learning without real data. Things like, say, data privacy and medical images, and the challenge of building up these large unlabeled data sets where, say, in the Scaling Transformers paper, Google now has this JFT 3 billion. So this idea of democratic research and doing self-supervised learning research, 3 billion images that are curated like that may be hard to attain and so on. So maybe this kind of paradigm makes it easier to do self-supervised learning research. We have two new papers from researchers at Google drilling into knowledge distillation. This first paper is titled Knowledge Distillation, A Good Teacher is Patient and Consistent. So this is trying to just unify this view of knowledge distillation and have a standard training procedure for how to compress models with knowledge distillation. So the key findings are this idea of viewing knowledge distillation as function matching, where the student is trying to match the function of the teacher, and how it helps to use mix-up and use the same exact crop that's passed to the teacher and the student. So this is illustrating the differences. So say this black outline is the entire image that's passed to the teacher, whereas this crop of the face is passed to the student, and now they're matching the logits on the two different views of the original image, or say it's two different crops. So then consistent teaching is they both see the same crop of the image, and then function matching is increasing the support of the distribution by using the mix-up augmentation. Mix-up is where you say take this rabbit or cat image, and then you say sample a deer, and then you mix the two, if this is CFAR10 or something like that. So mix-up, you average the pixels out of two images, and then you produce these kind of blurry images like this. That increases the support of the distribution and is a pretty strong data augmentation strategy. So they show how this also helps. So this is the idea behind consistent teaching. The next idea is patient teaching, and patient teaching is referring to long training schedules. So they train it for, say, 10,000 epochs of matching the student with the teacher. So that's the idea behind the patient teaching and long training curriculum. So patient teaching is showing the improvement. Function matching continuing to improve as you get up to, say, 9,000 epochs, which is obviously a long time for training. So they are able to improve the ResNet 50 by, say, 2.2%, I think it is, over the last state-of-the-art ResNet 50 model through distilling the BIT large model with these techniques. And then they describe some other techniques like the shampoo optimizer and how that improves its training efficiency at around from 4,800 to 1,200. And then other things like, say, going from a BIT model to a MobileNet, which is a totally different architecture. And they describe things like, say, group normalization versus batch normalization, how do you have these kind of differences that make it hard to transfer model families. And that's some of their motivation behind, with the overall objective of compression being what you want to do. You have model pruning and knowledge distillation. You also have quantization, which they don't mention, but more of a hardware detail. And then so model pruning, they describe, can be restrictive because it doesn't let you change from, say, a ResNet to a MobileNet with completely different components like depth-wise separable convolutions, or more particularly what they describe, say, if it goes from group normalization layers where you have to have this different way of balancing the features and so on. So overall motivating knowledge distillation, proposing this consistent and patient approach, and then showing the state-of-the-art on compressing a BIT model into a ResNet 50. And one last detail that I think is interesting from the paper is that they describe how they have the download counts of the TensorFlow hub, and that the ResNet 50 is downloaded significantly more than the BIT models. Or I think it would also be interesting to see maybe the efficient net that's maybe like a little more marketed. A little more people, I think, would know about the efficient net model than the BIT model. but they describe how the ResNet 50 is usually what people go to, and that's what I also use. I like the ResNet 50, so it's interesting to see that kind of detail as well. The next paper is asking, does knowledge distillation really work? And what they mean by really work is not that does it improve student generalization, because clearly it does with these different experiments that have come out to show that the last paper just showing that you can improve the ResNet 50 through knowledge distillation. But what it's asking is the student actually able to match the teacher? And what they find is that this is actually an extremely difficult optimization task, and the student doesn't actually match the teacher, even though it still does increase the generalization ability. So this blue plot is the maximizing the teacher agreement, and then the student generalization ability. So they show that in this particular setting where you have an ensemble of 3 teacher models, as you increase the agreement, it doesn't necessarily increase the generalization of the student model. So they're showing that they can actually be competing tasks. And it's one interesting thing that they note is about how the self-training with noisy student thing, when you're cloning the same exact architecture. So in self-training with noisy student, this idea of self-training generally, in noisy student, they actually do increase the size of the student model relative to the teacher. But this idea of transferring from the exact same architecture is saying that these are competing objectives. Exactly matching the teacher and then improving upon generalization are 2 competing objectives with respect to the optimization task. So they have these different control experiments with the MNIST dataset and then the CFAR10, and using GAN sample data for probing into this idea of distillation and fidelity, which is how they term this idea of matching the student and teacher labels. More details of why we might be interested in this, and then different hypotheses about why it is that it's hard to match this teacher labels, data augmentation, data recycling, and then optimization challenges, increasing the amount of data by the use of GAN, so similar to, say, the deep bootstrap framework where they generate data from a generative model to have more data to study these kind of ideas, and so on. So overall, an interesting study, an interesting problem with respect to knowledge distillation, and an interesting characteristic to study further with this learning algorithm. AdaMatch, a unified approach to semi-supervised learning and domain adaptation, is the latest installment in the series of the remix match and fixed match algorithm. So the high-level overview of this algorithm is that we're in the semi-supervised learning setting where we have a small set of labeled data and then a large set of unlabeled data. So what we're going to be doing is we're going to be trying to align predictions of weak augmentations and strong augmentations. So as shown in this image, a weak augmentation would be, say, like a slight rotation or translation of the pixels, whereas a strong augmentation would be like rotating it, say, more than 40 degrees, changing the color of the image, and so on, all these different data augmentations. Strong being higher magnitude, maybe more augmentations stacked sequentially as well. So we try to align the label distributions of the target of the weak and the strong in order to have this structure, this loss function. So there are a lot of other details with this. You have the distribution alignment. This is related to class imbalance, where you want to have the alignment of the predicted labels on the labeled data to match the unlabeled data prediction. So that's the idea of matching the class label distribution, and then you have the relative confidence threshold, where if there's too much entropy in the distribution of the labels, you just throw out this example, you don't learn from it. So you have this, it has to be at least this confident, and then you would assign this one hot encoded pseudo label to match the strong. So this is the overall pipeline of how these gradients flow and how these different loss functions propagate back. And so on, this is the framework of AdaMatch, building on fixed match and these other ideas. So the other key idea of this paper is to unify semi-supervised learning and domain adaptation. So domain adaptation and this data set, the domain net, is this idea of trying to transfer from a source domain to a target domain. So the authors note that this transfer from a source domain to a target domain is similar to this setting of semi-supervised learning with a labeled data set to an unlabeled data set. And they also note the semi-supervised domain adaptation, where you might have some labels in the target domain as you're doing the source to target domain transfer. So they evaluate the algorithm, they make these changes to the fixed match algorithm, different ideas in how you sample augmentation, particularly the batch normalization change, random logit interpolation, way of structuring the logits for this part of it, distribution alignment, and then changes to distribution alignment itself with this normalization of the pseudo labels, and then also a dynamic curriculum of the confidence threshold. So this C value for the confidence threshold isn't fixed throughout training, it evolves over time. Another interesting detail is that it's pretty robust to the hyperparameter searching through it. So you don't need to really tune the temperature on the distillation or the ratio of the unlabeled data to labeled data in the sampling as it goes through this pipeline. So they evaluated on these domain adaptation data sets, Digit 5 and DomainNet. They tested on 64 by 64 to make it easier to compete with the algorithm and explore different ideas with less computational resources. These are results of AdaMatch compared to having the labels, and then compared with other different strategies. Next up, we have a pretty interesting idea for contrastive learning titled self-damaging contrastive learning. So the key insight from this paper is about what do pruned neural networks forget. So we see that we can prune a neural network, have this sparsity, say 5% sparsity only causes accuracy to go from 80% to 77%, as I said previously. But so this paper from Hooker et al. explores what does it forget exactly as you prune the network. So this paper is proposing, and what they find is that it's the long-tailed, the class imbalance, the minority examples that are forgotten when you're doing this pruning, as it's as we've seen in previous papers like the simplicity bias. Stochastic gradient descent is biased towards these easy solutions, so it makes a lot of sense that and there's this class imbalance problem and so on. So it's not a super surprising result. But what they're showing here is a strategy to utilize this information for learning the long tail distribution for self-supervised learning. So it's similar to bootstrap your own latent, whereas instead of having this momentum running average of the target network's weights, it's a compressed version of the target network. So see how the self-competitor has been pruned. This is obviously a simplistic diagram. There are much higher capacity models in this, and then this is how you use the representation entropy, and this helps with this hard negative mining because only the long tail distribution, say dogs are, just pretending that this is a very rare example, that dogs appear in this data set of, say, Google Images or wherever you'd find a large unlabeled data set for self-supervised learning, and then it would have a higher loss because it's formed some high entropy distribution over the representation, and it's much similar from the non-pruned version. And this is how they structure the loss function and help with this problem of class imbalance in self-supervised learning long-tail distributions. The next advancement in self-supervised learning this week is MST masked self-supervised transformer for visual representation. And also new this week, and will be covered in next week's AI Weekly Update video, is the BEIT BERT pre-training of image transformers that's showing a really remarkable ImageNet result, 86.3%, only using this VIT large model, not this super 2 billion model or a very large model, but using this pre-training task similar to BERT. So the idea is, how can we use the BERT denoising autoencoder objective, where we mask out tokens in natural language processing and then predict the masked out tokens? How can we apply this to masking out pixels and predicting the masked out pixels? And say that's kind of what generative adversarial networks do, where they compress it and they predict the reconstructed image. Well, it's not as much context. Is a better example is, say, the image GPT. Image GPT is, say, the autoregressive left to right thing of predicting the pixels that have been masked out left to right as you traverse through a pixel window, whereas BERT is the denoising autoencoder objective. So this hasn't worked well when you just try to mask out pixels and say, like, you mask out any random pixel sampled from the pixel grid. So what they're proposing in this paper is similar to knowledge distillation. You use the attention map from the teacher network in order to guide the masking out. So you want to mask out entire regions, but you also don't want to do it too aggressively and so on. So they use the teacher's attention mask in order to guide this masking to transfer this objective and then learn representations through the same BERT style pre-training strategy. And overall, this idea of trying to find out the best pre-training strategies remains to be a hot area of research in self-supervised learning. We also have another advancement this week in the state of trying to train generative adversarial networks with small data sets. So say we only have 2,000 images or less, and we still want to train a generative adversarial network, and then notoriously deep learning struggles with learning from small data sets. So the strategy here is to have a secondary loss function that is instance discrimination that tries to push the representations of all points from the discriminator and the generator far away from each other. So I'm surprised to see this kind of extra loss function given all of the different algorithms that have been proposed for training GANs with limited data and the complexity behind some of these, and then the results and so on, comparing it with, say, the adaptive discriminator augmentation model and so on. But overall, what's interesting is the results on this. So these are the 2K, 10K, 140K with the FFHQ face image dataset, and then evaluated with the for Shea-inception distance score, which is where you take the generated images, embed them into a feature space, and compare the distance between these generated image features with real image features on, say, like a pre-trained classifier. So this is the performance compared to these previous algorithms. And overall, this problem of trying to learn generative models with small data sets, I think is really interesting because you can then use them for data augmentation and then kind of have the classifiers learn from big data that's been sampled from these generative models. Next up, we have 2 new papers on advances in neural architectures. And generally keeping up with the state of deep learning every week and seeing all these new subtle architectural changes, I'm pretty burnt out on the topic of these slight changes to the vision transformers, like say the token-in-token transformer, or all these different ideas of how exactly you're going to structure the backbone of alternating attention and convolution, or all these different ideas. Overall, I don't think it's that interesting, especially just seeing how quickly these little changes make such a difference every single week. But these 2 papers are pretty different ideas, particularly this one, scaling vision transformers. It isn't just like a small change to the VIT model. It's about what happens as you scale it up to 2 billion parameters and even more pre-training data, and that's extremely interesting as well. They use 3 billion images in the JFT dataset, usually the JFT 300 million, now it looks like it's 3 billion images. And they describe how they scale this up from different ranges, 5 million to 2 billion parameters, 30 million to 3 billion training images, and then 1 TPU core day to 10,000 core days. So, and I think also this data set does have some kind of labeling structure similar to image, and I think they describe something like that. So, so overall, they showed these, saturating power law, scaling curves of the relationship, similar to these like laws, neural scaling laws papers from OpenAI, where they show these, the plotting out what happens as you increase the compute, dataset size, and model size. Similar lesson from train large then compress. If you have this fixed budget, it's probably best to increase the size of your model. All these other different kinds of takeaways from the study. And then, so the big models are more sample efficient. This is probably what I think is the most interesting takeaway. You can see the results by going through the paper. And then they come up with some new training strategies. A lot of these papers have some kind of, here's the technical details of how we made this work. Weight decay changes, changes to the class token, the CLS token on the vision transformer design, how exactly to scale up the data set. This JFT 3 billion data set is annotated with a class hierarchy of around 30K labels. So I didn't with a semi-automatic pipeline, so maybe that's some kind of weekly supervised label propagation pipeline, but still interesting to see this kind of data set. Next up, we have CoAtNet, marrying convolution and attention for all data sizes. And as I mentioned previously, I'm definitely filled my appetite with this kind of paper topic of exactly this subtle design between how you alternate between convolutions and attentions in the backbone, how exactly you're going to design attention for computer vision and so on, the feed-forward layers, the normalization, all that kind of ideas. I definitely am not particularly interested in it anymore, but this CoAtNet is probably the most rigorous study of these kinds of ideas. So first, they designed this new merging convolution and self-attention, depth-wise convolution over the thing, self-attention, this kind of way of structuring the features, and so on. And then they have, how exactly you're structuring the backbone. But then, so the experimental results is where I think the paper is really interesting. So they have the results over all these different scales of how many layers. The D is the hidden dimension of the blocks. And then they have the data augmentation regularization, how that impacts training. Results on ImageNet, comparison with all these different models, EfficientNet, normalization-free networks, data-efficient image transformer, vision transformers, all these different models that have been coming out so quickly that have caused this topic to be kind of chaotic in my opinion. And then, so parameters, computation, how long it takes to train it, and then the resulting accuracy. So again, ImageNet accuracy getting better and better as a result of scaling up these model architectures and drilling into the details of them, which is I'm not saying it's not productive, I'm just saying keeping up with the details of it is exhausting. So here are more results if you're interested in looking through the paper. So next up, OpenAI has a new paper on improving language model behavior by training on a curated data set. So these large language models like GPT-3, they're trained on just scraping the web where you get some awful data in there and then it's reflected on the output of the models. So they highlight all these different topic categories that they're trying to remedy with this curated data set. So they create a curated data set. It's much small. This is probably the most interesting technical detail is that they have 80 text samples, each sample with a question answer format between 40 and 340 words. And then the data set is much smaller than what's used to train the GPT-3 model. But GPT-3 is still able to adapt to this values targeted data set. So then when they evaluate the data set, they find that fine tuning it on this data set does work. And you see I think this value is targeted as once it's been fine-tuned, it also seems to improve with model scale, how well it can adapt to the new fine-tuning, which is a very interesting detail. Next up in the space of language models is dynamic language models for continuously evolving content. So the content of the web is in a constant state of flux, new entities, issues, and ideas continuously emerge, while the semantics of the existing conversation topics gradually shift. In a previous AI Weekly Update video, we looked at the vitamin C benchmark for fact verification dataset. So fact verification, they take as input a claim and then an evidence pair, and then they classify it as supported, refuted, or not enough information. And in this vitamin C paper, they explore how, say, the evidence changes over time. So as the evidence changes, you want to update the fact verification model that retrieves the evidence, retrieves the most recent evidence, and then updates its representations for classifying these claim evidence pairs. And this is looking at language modeling continuously evolving content. So they study 2013 to 2019 Twitter, where you don't have mentions of, say, COVID and Zoom in the as they describe how this is added to the dictionary. So the key idea is two sources of deterioration of the models: the semantic shift of existing tokens, so what existing words mean change over time, and then new tokens added to the vocabulary. So describe how to replace tokens in the vocabulary. Say the frequency changes, so you take it out and then put in a new token to keep that same fixed size of 30,000 tokens, and so on these different algorithms. So I haven't read too much about this paper, but I think this is a very interesting research idea of exploring how these models behave as the data evolves over time. One of the most exciting trends in deep learning and AI has been the open sourcing of the GPT-Neo model. GPT-Neo is trained on the Pile dataset, has an interesting composition of data, as we'll look at later with the diagram of, say, comparing what GPT-3 is trained on with the Pile dataset and what these resulting GPT-Neo models are trained on. And it's really exciting for doing few-shot learning research because you can access these models easily. Everyone can access them. So the latest model is GPT-J6B, a 6 billion JAX-based transformer model. So JAX is a more efficient way of training these models. You can access it with a Colab notebook or a free web demo to test things like as they show later. Say you want to test these prompts and see what the output of the model would be. So they describe how it takes 5 weeks training with TPU v3 256 cores. Definitely an interesting detail. Looking at this table, comparing the language modeling perplexity, this is how they evaluate how well they're performing the language modeling task with zero few-shot inference on these different supervised learning tasks. Slight modifications to the GPT-3 architecture in this design. Next up, we have a new survey on how data augmentation is being applied to natural language processing. The authors divide this into 4 high-level categories. Token level augmentation, where we say replace words or tokens with random insertion, swapping, using dictionaries, using language models to swipe out these replacing tokens. Other ideas like sentence level augmentation, adversarial data augmentation, and hidden space augmentation. That's how they choose to organize all the different augmentations for text data. They document the use of consistency training, where you try to, when say you have unlabeled data, like when you do back translation and you try to have this consistency property of the augmented data and the original data, showing a lot of different empirical studies of how data augment. Oh, sorry, this is their own. And then they unify all the different methods they survey into a study on news classification and topic classification to highlight that no free lunch with the data augmentations. And I think overall they highlight 3 key takeaways from their study. In the top, they summarize the data augmentations, or sorry, this isn't the, so this is the takeaways from their experimental results. Token level augmentations work well for supervised learning. Sentence level augmentations usually work best for semi-supervised learning, and augmentation methods can sometimes hurt performance even in the semi-supervised setting. So overall, another interesting survey of looking at how data augmentation is being applied to natural language processing and text data. Next up, we have meta-learning with fewer tasks through task interpolation. So the authors are describing how in order to do this meta-learning, you need a dense sampling of possible tasks. So similar to this idea that deep learning needs big data to learn for supervised learning, in order to do this meta-learning quick adaptation, it needs a large set of potential tasks in order to learn how to do that from. So I think a good example to describe it is the Omniglot dataset. It's something like 20 different alphabets with each alphabet containing something like 50 characters, or probably 50 alphabets with 20 characters, something like that. So you'd sample 5 random characters and then maybe have 3 to 5 images for each of the characters, and you have to learn to assemble these new labels for this new sampling of the Omniglot space. So a dense sampling of that would mean you've sampled several different combinations of the 5 characters to form this new task, and so it has this dense sampling of the task. So the idea here is a data augmentation scheme at the meta level, at the task level. And so what they're proposing is to use mix-up augmentation for the tasks themselves. So this involves doing mix-up where you average the images, the pixels of the images, as well as, say, the label space. And they describe the different changes for label sharing, non-label sharing, task overlap, and so on, if you're interested in technical details of this paper. But a very interesting conceptual framework, as far as I understand the paper, of this idea that you need to have data augmentation at the task level to perform well on this meta-learning idea. Next up, we have exploring the limits of out-of-distribution detection. This is when, say, a model has been trained on CFAR 100, and then it's presented with a Street View house number image, and it has to classify this as out-of-distribution. So it's not quite like having to generalize to classifying the labels of some new distribution. It just has to detect that it's out of the distribution, and overall it's a challenging problem where you want a deep learning model not to confidently misclassify some new image, but to say this is out of the distribution of what I've been trained on, or some idea like that. So I think the high-level overview of this paper is showing that these latest models like the Vision Transformer and so on are performing better at this without too much fine-tuning needed. So I haven't read too much about this paper, but I think it's a very interesting problem of out-of-distribution detection and this challenge for these models. So next up, we have two very exciting papers for how to unify causal inference and these ideas of causal learning with deep learning. I've been inspired by a lot of books and papers and courses. The Judea Pearl's Book of Why, Yashu Benjo and others have written this paper, Causal Representation Learning, and Brady Neal has a great course on causal inference available on YouTube. So all these things have made I'm really curious about causal inference and how it can be unified with deep learning. So here are two very interesting papers, I think, towards this direction. So the first of which, Self-Supervised Learning with Data Augmentations, provably isolates content from style. So this is taking this perspective of having this latent variable model where style is this confounding thing, and then you have the content. And so you can try to apply these interventions on the style through augmentation in order to disassociate content from style, and have the causal factor of how the content contributes to the annotation of the image or text sequence or whatever it is. And so I think this is a similar idea, and I'm not an expert on this at all. I think this is the idea of where you have more than one label, and so kind of similar how you separate the content and the style, you can blur out the different labels to try to get different views and apply different kinds of interventions. And having data augmentation or having the label augmentation, I guess, or this kind of multiple labels is kind of the interface for how you apply interventions on data to do this kind of causal learning with this kind of structure. So I don't know too much. I'm very curious about this topic, but definitely not an expert. And I think these are two interesting papers that make contributions in this space. So the headline breakthrough in AI this week is a graph placement methodology for fast chip design using reinforcement learning and graph neural networks in order to solve this task of chip placement. So I'm not going to comment too much. I haven't read the paper and I don't understand really this problem of chip placement, but it's very interesting to see this idea of using machine learning, deep learning to optimize the design of the chips that then do deep learning. And I don't know exactly where they quote this in the paper, but there was this one very interesting article I'd read about the challenge of designing these chips when they don't know the architecture. They can't exactly customize it for it. So say they have this development window of 2 to 5 years, but then they develop the chip and the architecture thing has changed, so it's not really optimized for the chip anymore. So having a faster turnaround for designing these chips, as they describe, generating these floor plans in under 6 hours compared to months of intense effort by human experts. So this should lead to a huge change in how these chips are customized for the different architectures. I think it could be even as fine-grained as a chip that's customized to an architecture, like the Vision Transformer and all that kind of stuff. But again, I'm not an expert on this, but this is probably the big headline advancement in AI this week. So also in the scope of reinforcement learning, we have two interesting papers on the representation learning aspect of reinforcement learning and how that helps to improve data efficiency. So say you're trying to learn your representation of high-dimensional visual inputs like pixel grids only from Q-learning and the sparse reward signal of, say, grasping tasks or pick and place or all these different ideas. It helps to have this auxiliary self-supervised learning task. So this first paper is exploring 3 different tasks with which they intuitively motivate as these self-supervised learning questions you can ask with these state, action, next state reward sequences. If I take action A in state S, what state S prime am I likely to see next? This is like the generative model, predict the action state transition to the next state. If I transition from state S to state S prime, what action did I take? This is like the inverse dynamics question. What action A would I take in state S so that I reach another state S prime as soon as possible? This is this goal conditioned setting of where you want to reach some particular goal. It could be some particular amount of reward or some particular state. So these are different self-supervised learning tasks that they can structure to improve the representation learning, and particularly this benchmark of Atari with 100,000 steps of interaction, which is equivalent to 2 hours of human experience, and overall learning to learn fast with reinforced learning agents. And then I believe this is another study with similar ideas that I haven't read too much about, but another paper on this topic of learning these encodings, representations of the states for control tasks. One of the most interesting trends in deep learning has been to move all these advances in natural language processing to processing text code data. So say Python code, documentation search, and all these kinds of ideas. So the CodeXGLUE benchmark is a collection of different tasks that you can perform with code data. So natural language code search, say documentation generation, or code completion, close testing to see what kind of knowledge is retained, or duplicate code detection. So now it's all been unified in the HuggingFace Dataset interface to load and test these datasets for yourself. So again, with the release of these models like GPT-Neo and GPT-J, it's going to be really interesting to do research on zero-shot generalization and few-shot generalization with examples in the context input window. And so here's a notebook showing you how to do zero-shot text classification with the HuggingFace pipeline object. So you just do pipeline, zero-shot classification, pass and labels as is described in this blog post, and you can test this idea of doing zero-shot text classification, which I think is a really interesting area of research that's emerging and becoming more accessible with things like the HuggingFace pipeline and then these models like GPT-Neo. So on the topic of, say, unpacking HuggingFace's pipeline interface and all the different things that you can do with the HuggingFace transformers, datasets, libraries, and all the different navigations of these tools, they've released a course. So this course has all these different aspects. It's really exciting. I haven't completely gone through it myself, but it looks like a really exciting course for understanding how to use HuggingFace and take advantage of all these amazing things to do research in not only natural language processing as they're moving into computer vision and all this kind of thing, these kind of things of deep learning. So again, just to quickly present this, here's a tutorial on graph regularization for sentiment classification using synthesized graphs, showing you how to implement neural structured learning for text sentiment classification, this interesting idea of having this graph regularization for the loss function in deep learning. Here's a diagram comparing the data that GPT-3 is trained on compared to the GPT-Neo model with the PILE dataset. So I think this is a really interesting diagram. I'm not sure who the original author of this is. I'll link the tweet that how I came across this, but I think these kind of diagrams are very interesting for taking apart these language models and the insides of how they've been trained. So the common crawl corpus, you see how it makes up a large percentage of GPT-3 and a small percentage of GPT-Neo. This has to be pretty noisy data. This is, say, like the C4, the common crawl colossal corpus, where they just kind of scrape the internet. Reddit data making up 19% of it. And then say books 2, and Wikipedia. So this is Wikipedia. This is probably the better data. Overall, compared to all these different ways that data is constructed for the GPT-Neo model, I think it's interesting to see these compositions of the different data. And I imagine that in the future we'll see these kinds of diagrams, maybe not as people, but as like a database diagram, and then more fine-grained of looking through different kinds of data sources as we compose the data sets for training these language models and knowledge-intensive natural language processing systems. So next up, a new paper towards natural audio to video generation with representation learning. This is a really interesting success of being able to translate from audio into the video generation. Very interesting data source of using the HBO Last Week Tonight with John Oliver show, as you have this format where you have a large data set, you'd imagine, of the paired audio with the video data and being able to learn this mapping. So I think this is a really exciting model, very interesting in the space of, say, deep fakes and all that kind of, definitely something to be aware of how you can generate this kind of data. It definitely will create some problems with it. And overall, maybe for data augmentation and representation learning and all these advances in video generation, a very interesting space and a data modality of doing deep learning. So finally, here are a couple of the data sets that have been added to PaperswithCode Datasets: the SEDE, Stack Exchange Data Explorer, the text to SQL task of trying to take the title, description, and then translate it into SQL code for database queries, and then also value, a multitask benchmark for video and language understanding evaluation, doing things like text to video retrieval, video question answering, and video captioning, and all these benchmarks being added to the PaperswithCode Dataset section. Thank you so much for watching the latest AI Weekly Update from Henry AI Labs up to the week of June 16th, 2021. Please subscribe for more deep learning and AI videos, and I hope you found something interesting to read from this curation of the new content in deep learning and AI this week.